Hello, welcome to Target IES. I am Prakash Rajput. So today we are studying power system and we will see the objectives of transmission. If you have gone through the previous lectures, which was of the power system, so it is already told that what are the objectives of this transmission. What are the objectives of transmission? The first one is that the transmission line should have maximum power transfer capability. Maximum power transfer capability that should be it should be handled to it should be able to handle, and it should be able to transmit large amount of power from sending end to receiving end, and that too with minimum losses and that too with minimum losses. So we can also say that in this that with having high efficiency and high efficiency. So as losses will reduce, obviously it will have high efficiency, right? And the second objective is that the voltage regulation should be minimum, or if possible it should be zero or minimum possible. Like there should be not a large amount of voltage drop from the sending end to receiving end. It should be ideally zero, and it should be not very low. Okay, I mean the voltage at the receiving end should not drop by a very large amount, because it will affect the supply, and it will cause more losses. Because if the voltage will be low at the receiving end, then it will require more current, and that will obviously increase the losses in the transmission line, and we will fail to achieve these objectives if this happens. So let us see that how can these objectives are fulfilled. So we will see one by one that how this first one, that is maximum power transfer capability, is done. Okay, so objective 1. So if you consider a short transmission line, so here is my receiving end having some sending end voltage. So I'm considering a short transmission line, so only inductance will be considered, as you know, for a short transmission line. And suppose here is my receiving end having some voltage VR. Okay, and here if I connect a load like this is my load. So you know that for a short transmission line, as there is no resistance, we can say the sending end power in the receiving end power are equals to Vs Vr by XL by into sine delta, right? If you have seen the power equations of this PR and receiving power and sending end power. So this right now we are doing objective one analysis, that how can we make the this power maximum. We have to increase this power transfer capability. So there are three parameters basically. So let us say if I take the VR, if I take VR and Vs equal, so this power transfer will become what? Vs square by XL sine delta. I'm considering just magnitudes here. So as you can see that this sending end power is what is proportional to square of the voltage, is proportional to, first thing is that Ps is directly proportional to, or if I directly write this is magnitude, directly proportional to square of the voltage. So that is why we will have higher voltage rating for transmission line, high voltage रेटिंग फॉर ट्रांसमिशन लाइन, क्योंकि अगर हाई वोल्टेज रेटिंग होगी तो हम ज्यादा से ज्यादा पावर ट्रांसफर कर पाएंगे. इससे क्या होगा? पावर ट्रांसफर capability will increase. Power transfer capability will increase. Also, if this voltage is higher and higher, there will be a reduction in loss. How this will be? So let us see how the current will reduce. So that we can take as the loss in the transmission line as what, the current flowing in the transmission line multiplied with the resistance of the transmission line. Okay, so as you can see, and also you know that P is equals to VI. Here this P is basically the power which is flowing through the transmission line. P is equals to VI cos phi, right? And if I take the I value, that will come as P by V cos phi, right? P by V cos phi. So if I put the value of I here in the loss term, power loss term, PL is basically what, loss in the transmission line. So this will become what, P by V cos phi, right? P by V cos phi square into R. Now as you see that here this V is what, this V is nothing but the sending end voltage. So this we can see that PL is directly proportional to Vs square. So as you increase the voltage, higher and higher, then losses will reduce at a very faster rate. That is because here it is proportional to square of the voltage. Here it is proportional to square of the voltage. Here we are considering what, that P cos phi and the value of resistance are constant. Okay, the sending end power is constant, the power factor is constant, and the resistance of the line is constant. So we are assuming that, so with higher voltage, the power loss will reduce, but we cannot go beyond a certain limit. There are also limitations on that part also, that we will see. Now as you can see that what, the with high voltage the power transfer capability is increased, right? And the losses are reduced. Okay, so also there is one more thing, that in the designing aspect of the transmission line, if you see the value of R from here, if we consider all the things constant like this part, so R value will be what, PL into V square cos square phi uh, divided by P square, right? So I can write it here, R equals to, I write this, so R is equals to PL into V square cos square phi divided by P square, right? And you know that R is equals to rho L by A. R is equals to rho L by A, where L is what, length of the transmission line, A is what, area of the cross section of the transmission line. Here A is equals to rho L by R. Now if I put the value of R here, this will become what, rho L divided by R. R value will be what, this. So here it will be PL into V square cos square phi and into P square. So if you see this thing, and here this resistivity, the length of the transmission line, the sending end power, if you consider them constant, and this loss will also be considered as constant, then what happens? If we consider that the resistivity of the transmission line, length of the transmission line, sending end power of the transmission line, the loss are we are taking as constant, then what happens, the area of the cross section of the transmission line is proportional to voltage square into cos square phi, right? So here you can see that with increase in voltage, with increase in voltage with increase in voltage, what happens, with increase in voltage what happens, or with increase in power factor also you can say, okay, but just now we are considering the voltage term. So if we say that the voltage we are doing higher and higher for the transmission line to make it to make the power transfer maximum or higher value, so what happen is area of the cross section of the transmission line is also reducing, right? अगर area of cross section reduce होगा तो उससे क्या होगा, volume of the conductor required will also be reducing. So volume will is what, volume is area into length. Length we are considering as constant. So as you know that volume will also be proportional to 1 by v square. So as the voltage increases, this volume will go down, and volume अगर कम होगा तो cost of the transmission line, cost of transmission line will reduce. So we are getting many benefits with higher voltage of the transmission line, right? The losses are getting reduced, power transfer capability are getting maximized, and the volume of the conductor we require is getting reduced. So there are like many number of advantages by increasing the transmission level voltage, right? But we don't go much above a certain value, like the maximum voltage limit is 765 kV. Beyond that, beyond 765 kV, what happens, there will be requirement of more insulation, and this will basically increase the cost, right? This will basically increase the cost. More insulation is required, which will increase the cost, which will increase the cost. This is basically, we can say, limitation. We cannot go beyond like go to like very high values and we keep on going, nothing like that. So we have to put some limitation, we have to stop somewhere. So this is the maximum limit. Otherwise we have like uh, we go like 400 kV lines are there, right? So that was about the uh, higher voltage concept. Now the power transfer was not only proportional to v square, just what was that, p is equals to v square by xl into sine delta. Here it is proportional to the inductance or reactance, we can say also. So if we decrease the value of inductance, we will have a high amount of power transfer, right? We will have a high amount of power transfer. So there are various methods for reducing this value of inductance. So the first method is, we will write methods of reducing XL, the transmission line inductance. So we can use, I mean you can do what, कि आपको इंडक्टेंस अगर कम करना है किस चीज का, तो आप नेटवर्क का कॉन्सेप्ट लगा सकते हो, दैट यू कैन यूज कैपेसिटर, you can use series capacitor to do this. So that is not very often thing. We have a different thing, like we can connect parallel connections. Parallel connection से क्या होगा, inductance reduce होगा. So we can use first that by using parallel, or we say that as double circuit line, double circuit line to reduce XL, to reduce XL. ठीक है, इस बात को आप ऐसे समझ सकते हो कि अगर दो ट्रांसमिशन लाइन है या दो इस तरीके से कुछ सेक्शन है, ठीक है, इसकी इंडक्टेंस लेट्स से J.5, इसकी इंडक्टेंस भी J.5. here if suppose this one angle 30 degree is there and is let us say here one angle 0 is there, so the power transfer is what for this, it has 1 into 1 by the inductance of this part will be what, 0.25, right? 0.25, half of this value, and into sine 30 degree. So we can solve this part as what, 2 will come, right? But if there was a single circuit line, if there was a single transmission line with same specification, the sending end voltage is 1 angle 30 degree, receiving end voltage is 1 angle 0 degree, Here the transmission line inductance reactance value is j.5. So the power transfer will be what, 1 into 1 by 0.5 into sine 30 degree. So you can see that here only just 1 per unit, right, 1 per unit. So you can see that in this part, the first part, in the second part, the power transfer is increased compared to this. So how this has increased? This has increased by reducing the value of XL. By reducing the value of XL, we can increase the power transfer capability of the transmission line. Second part is what? We can use series capacitor. Using series capacitor. Okay, so we have to connect series capacitor in the series of the transmission line. So that will what? That will uh, cancel the some part of this inductance, right? If this is a transmission line of some value j.5 and we have connected a capacitor of some value like j 0.2, so what will be the effective XL that we will take? That will be 0.5 minus 0.2 is equals to 0.3. So obviously the power transfer will increase, right? So in this way we can increase the power transfer capability. So this series capacitor thing is known as series compensation of the transmission line. Series compensation. Okay, this is known as series compensation with connecting a capacitor in the series. Okay, third thing for reducing the value of XL is using bundle conductor. Using bundle conductor. Using bundled conductor, we can reduce the value of XL and have a greater value of power transfer. So what happens in bundle conductor, we will see in detail in the part of the like parameters of the transmission line, in that we will see how to find the value of inductance and the capacitance of the transmission line. So just now we can say that in bundle conductor the effective radius of the conductor effective radius of the conductor is increased. Effective radius of conductor is increased, which will basically reduce the value of L, which will reduce the value of L, and thereby XL getting reduced, and thereby what happens? Power transfer increases. Power transfer increases. Okay, now there was another thing we can use to maximize the power, that was here sine delta, right? So if we increase the value of delta, then what happens? Then also the power transfer capability will increase, right? So here Vs square by XL sine delta. So if delta increases, this power transfer capability will also increase. But we cannot increase the value of delta above a certain limit because of stability concern. So we cannot increase the value of delta for stability concern. This delta value is limited to up to 55 degree, up to 55 or 50 degree, we can say 50 to 55 degree, it is limited. Okay, beyond that if we increase the value of delta, there will be stability concern that we will deal in the stability part of this power system. Okay, so just now you can for right now you can remember this, that we cannot increase the value of delta above a certain limit, because that will basically affect the stability of the power system. So due to stability limitation, this maximum value of delta is around the 50 to 55 degree, we can say. So up to 50 to 55 degree due to stability limitation, right? So this was the part for the objective 1, where what happens, where we are increasing the we were increasing the power transfer capability of the transmission line. So this was basically the part for the objective 1. Now there was objective 2. Objective 2 was what? Objective 2, that voltage regulation of the transmission line should be minimum or zero. So voltage regulation कैसे निकालते हैं हम basically? Voltage regulation of the transmission line, if we see, the voltage regulation is given by Vs by A minus Vr divided by Vr into 100. This is percentage voltage regulation basically. Okay, this Vs by A minus Vr divided by Vr, where Vs by A is from, like, if you know the transmission line parameters like this, Vs Vr plus मतलब AVR plus BIR, right? So like this, they are there are the transmission line equation for the sending end voltage. Now for voltage regulation, what we do is, V no load, that is VR at no load minus VR at full load divided by VR at full load. That is how we find the voltage regulation, right? So here for no load, what happens is this IR becomes 0, so this part will not be there. So the VR at no load becomes what? Vs by A, right? So that's why this term Vs by A is there. So this is basically the formula that you can use for the part of voltage regulation, Vs by A minus Vr upon Vr into 100. Okay, you just have to consider the magnitude part. Okay, so how can we reduce this? So let us first do what? First we will see for different loads what happens to the sending end voltage. Okay, like we will draw phasors for different loads. We will draw phasors for different loads, unity power factor, leading power factor, lagging power factor, and we will see what is their difference between the sending end and the receiving end voltage, and then we will find a relation for finding the maximum voltage regulation, and how it can be minimized, and for what load it will be minimum, or it may become negative also. So we will see that. Okay, so let us first consider a transmission line. So for simplicity purpose, we can consider a short transmission line having a resistance also this time. Okay, here sending end voltage is Vs having a resistance and the inductance part. Okay, so here R and here XL, and the receiving end here. Now we will connect one by one different loads. So let us first consider the most common load, that is lagging load. Okay, so for lagging load, what happens if you take the phasor diagram here? I can make this as IR, here VR and VS. Okay, so as I'm making for a lagging power factor. Okay, so take the reference phasor as VR. This is my reference phasor. So as the current is lagging, so I can take this current as like this. This is IR, right? And this angle will be what? The receiving end power factor. Receiving end power factor angle. Receiving end power factor angle. So due to the resistance, there will be some drop of IR R, right? And due to the due to the inductance part, there will be some uh, like this drop due to inductance. Okay, so this will be what? IR XL. As you see that this is a short transmission line, so here IR and IS both are equal, right? So just you have to do what? The Vs is what for this? Vs is nothing but the VR angle 0 plus IR angle phi r and multiplied with r plus jxl, right? So I have to do what? I have to add all these, so I can make this joining to the tip of this red phasor. So this will give me what? The sending end voltage. Here you can simply see that Vs magnitude is greater than Vr. Vs magnitude is greater than Vr. And for a short transmission line, I have not written here. For a short transmission line, A is equals to 1. So this becomes just Vs minus Vr divided by Vr into 100, right? So directly we can see that Vs is greater than Vr, which means what? That the voltage regulation will be positive always for lagging load. For lagging load, the voltage regulation will always be positive. The receiving end voltage will always be less. Okay, so voltage regulation is always positive in the lagging power factor case. So if the load is lagging, the voltage regulation will be lagging always. Now let us consider the unity power factor load. Let us consider the unity power factor load. So here this is sending end, here this resistance and inductance, again here IES is going, here VS, here VR, and I have connected a resistive load, that will be a unity power factor load only. So again I will take reference phasor as VR, right? So as the unity power factor load is this, so the IR will be in phase of the VR. So here this will be IR. Now what happens to the drop of resistance? It will be IR into R, and this value, this will be a straight line. If I make here, this will be what? IRXL, or if I write JIRXL, in fact. So now if you join these two, this will give me what? VS. This will give me VS. So as you can simply see here also, the VS is always going to be greater than the VR. Vs is always going to be greater than Vr. Here also the voltage regulation is positive. Voltage regulation is positive in this case also. So for lagging power factor and for unity power factor, the voltage regulation is going to be positive only, because it will simply add these drops of the resistance and inductance, and then it becomes the sending end voltage. So always it is going to be more than the receiving end voltage. But there is a different thing for leading load. There is a different thing for the leading load. So let us take a leading load, and we can make the phasor diagram for that also. So let us first consider again this transmission line. Here it will be what? Vs. Here these will be RXL. Here IR, and a leading load. So for a leading load, there will be a capacitor, right? So this will be here IS, this will be receiving current IR. Both are equal for this transmission line which I have considered, right? Now let us make the phasor. So again we will take reference phasor as VR. Reference phasor as VR. Okay. So now what happens? This is leading power factor. Leading PF load लगा हुआ है. So for leading PF load, the current will be leading. The current will be leading, right? So this is IR. This is IR. Okay, and this angle will be between them will be phi r, the receiving power factor angle. Okay. So now the resistive drop will be in this phase, like, right here I can write IR into R. Now the inductive drop will be something like this JIR XL, right, 90 degree to this. Now if I join this, now if I join this, then what happens? You see that if I join this, I will get VS. And if you see the phasor diagram, then here Vs is less than Vr. Vs is less than Vr, but it is not always the case that Vs is going to be less than Vr. In case of leading power factor also, there can be Vs can be greater than Vr, or can be equal to Vr. But just for the understanding purpose right now, because the previous cases there were always going to, they were it will be like Vs is always going to be greater than the Vr. But in this case, in the leading power factor case, it can be either greater than the Vr, it can be lesser than the Vr. So if it is less than Vr, so what happen is voltage regulation can become negative. If it is equal, if it is equal, then voltage regulation can become zero also, right? And if it is greater, then voltage regulation can become positive. So here we can write that for leading PF, for leading power factor, voltage regulation of the transmission line can be positive, can be zero, can be negative also sometimes. Okay, so we want what? We want zero power factor. I mean zero voltage regulation. We don't want drop in the transmission line. Okay, just the voltage at the sending end, that will be the voltage at the receiving end, that we want in ideal conditions. Okay, so but our most of the loads are most of the loads are even we can say almost all loads are lagging, right? And this is happening at leading power factor, so we have to think of some alternatives for that. Okay, but here if the leading load is considered, then voltage regulation can become positive, zero, or negative, right? Now in some objective exams, they will be giving like the what is the voltage regulation formula, the condition for the maximum voltage regulation. For that we can derive that expression for the for which conditions that voltage regulation with lagging load, or voltage regulation will be maximum, right? So now we will see the condition for maximum voltage regulation with lagging load. So here the derivation for this part is not of much that importance. So you can just take, because you don't need to find the voltage regulation with using this formula which I am writing over here. You just simply use the our formula which we have told earlier, Vs by A minus Vr upon Vr. Okay, that will be sufficient for finding the voltage regulation. But just in case if you want to use this formula which I am writing, R cos phi r plus XL sin phi r, this is basically based on some approximations. Okay, and this will be used for the short transmission line upon Vr into 100. This is the formula for lagging load for voltage regulation to be find out, right? Now we are finding condition for maximum voltage regulation in the lagging load. Okay, this can be easily found out using the phasor which we have drawn, right? But in this case you have to draw the phasor with like with taking a reference of I. If you take a reference of I, then Vs will come somewhat here for lagging load. Okay, and the IR, the resistive drop, will be here, and this will be your inductive drop, and here this will be what? This will be the supply voltage, or the sending end voltage we can say. Okay, this will be Vs, here this will be Vr, this is the IR, and this will be JIR XL. So using these relation you can get to this formula by the simple formula. What was that? Vs minus Vr upon by Vr for the short transmission line. Okay, you can get to this expression which I have written here. Now we will see what the condition for maximum voltage regulation. So maximum voltage regulation के लिए क्या करना पड़ेगा आपको? For voltage regulation to be maximum, I have to differentiate this voltage regulation expression with respect to phi r. Okay, so here you can see that IES and VR are like constants. Okay, we are differentiating, we are partially differentiating with respect to phi r. So I can consider only this part, r cos phi r plus xl sin phi r, right? So I will do what? I will do del by del phi r, just the r cos phi r, because I have to put ultimately this I have to equate this to what? 0 sin phi r. This will be what? Equating to 0. So we will get what? We will get here, I will get r sin phi r plus xl cos phi r. So using this you will get the tan phi r equals to xl by r. Tan phi r equals to xl by r. So condition for maximum voltage regulation is nothing but this only, that power factor angle should be equal to tan inverse xl by r. Tan inverse xl by r. This I have to equate to 0, then I will get this. So this is the condition for maximum voltage regulation in case of lagging load. Condition for maximum voltage regulation, right? This is condition for maximum voltage regulation, where this phi r is what? Phi r is the power factor angle. Okay, power factor angle of the load, and tan inverse xl by r, where xl and r are the parameter of the line. ठीक है, ये transmission line inductance है, and ये inductance of the we can say what, um, the resistance of the transmission line, right? Now this is the condition for maximum voltage regulation. So there will be like if you know that for a lagging load, for a lagging load, or if you see this expression, this is what? Tan inverse xl by r. So this will give just the angle or the impedance angle of the transmission line, isn't it? This is giving just the angle of the transmission line, impedance angle of the transmission line, right? So we can say that for maximum voltage regulation, which we do not want, right? But we should know that at what condition this happens. So when this impedance angle of the transmission line will equal to the receiving end power factor, that is nothing but what? R by z, right? R by z. Z is what? R plus jxl, or I can write the magnitude r square plus xl square, or the angle theta. Theta is what? Tan inverse xl by r. It is same as this, right? So if the receiving power factor angle and the impedance angle of the transmission line will become equal, then what happens? The maximum voltage regulation condition occur, which we do not want. So if this power factor of the transmission line मतलब कि इस पावर फैक्टर पर ट्रांसमिशन लाइन को कभी ऑपरेट नहीं करना चाहिए, क्योंकि हमको मैक्सिमम वोल्टेज रेगुलेशन नहीं चाहिए. वी वांट voltage regulation to be minimum. So we can say that at this power factor, at this power factor, transmission line should never be operated. It should never be operated at this power factor, right? So now we will see a condition for voltage regulation to be 0. Voltage regulation to be 0. So voltage regulation 0 अगर रखना है तो क्या करना पड़ेगा? So we have to uh, we have seen that for the 0 voltage regulation we have to consider the leading power factor. So for leading loads, for leading loads. Just now I have written an expression for lagging load voltage regulation, leading load. In that expression I have to I have written what? IES R cos phi r minus, previously I have written plus sin phi r divided by VR into 100. So the change is that this plus sign is will be this plus sign will be replaced by minus for leading loads, for leading loads. So you can directly use this relation for leading loads, and careful about the sign part here. IS by VR into R cos phi r minus XL sin phi r, and for percentage regulation we can multiply this to 100. So अगर ये इसको जीरो करना है, so क्या करना पड़ेगा हमको? For this to be zero, for voltage regulation to be zero, I have to equate this part. I have to equate this part to be zero. Only then it will be it will become 0. R cos phi r minus XL sin phi r equals to 0. So I can say that the phi r will become what? Phi r will become what? Tan inverse r by XL, right? R by XL. So if you consider the uh, uh, I will write this as phi r is equals to tan inverse R by XL. Now if you want to write this in terms of impedance angle, so you can write this in that way also. So impedance angle will be what? Tan inverse XL by R, right? So we can write this as pi by 2 minus theta. Theta is what? Tan inverse XL by R. That is the impedance angle of the transmission line. So this is the condition for the zero voltage regulation. Condition for zero voltage रेगुलेशन. अगर जीरो वोल्टेज रेगुलेशन चाहिए तो ये कंडीशन रखनी चाहिए. द पावर फैक्टर शुड बी लाइक दिस. पावर फैक्टर ऑफ द रिसीविंग एंड शुड बी like this. It should be this 90 minus the impedance angle of the transmission line. थीटा क्या है? Impedance angle of the transmission line. Impedance angle of transmission line. Okay. So power factor of lead load. If you want to write the power factor for this load, then it will be what? It will be equals to uh, cos phi r. Phi r is what? Cos pi by 2 minus theta. For zero voltage regulation, that is nothing but sin theta. And sin theta we can write as XL by Z. Sin theta we can write as XL by Z. These these terms, these come for like objective questions. They will directly ask you for the expression, or if you remember the formula also, then it will be little easier or faster. You can do you can solve a problem. So this happens only in case of lead load. ठीक है, लीड लोड पर जीरो वोल्टेज रेगुलेशन हो सकता है. ओके, राइट. So just now we have done the analysis for the voltage regulation for the short line, right? But this analysis is also I mean we can say also uh, available, or also we can say for the lagging load and unity power factor load connected on the long and medium transmission line. They will also have voltage regulation positive. They will also have positive voltage regulation. Okay, so this is not just for the short transmission line, but the formula for that won't be used, this one which we have written like this, or this one. Okay, for them we can write the first expression which we have written, this one. This we can use for any transmission line. So we have to find Vs, Vr and A for any transmission line. short transmission line, we can use this for short transmission line, right? But the analysis which we have done, what was that? That with lagging and unity PF, unity power factor loads connected at the end, or the receiving end, we can say, at the end of the medium or long transmission line, medium or long transmission line, with lagging and unity PF load connected at the end of medium or long transmission line, has positive voltage regulation, has positive voltage regulation. It will be having voltage regulation positive until unless we will do like some compensation of this. Okay, so नॉर्मल लोडिंग पर, ठीक है, नॉर्मल लोडिंग पर बोल सकते हैं, ड्यूरिंग नॉर्मल लोडिंग और पीक लोडिंग, ठीक है, नॉर्मल लोडिंग और पीक लोडिंग यू कैन से, ठीक है, क्योंकि एक ऐसी कंडीशन है जहां पर नो लोड है, तो कभी कभी लॉन्ग ट्रांसमिशन लाइन पर रिसीविंग एंड वोल्टेज ज़्यादा हो जाती है, उसके बारे में भी देखेंगे, ठीक है। तो ड्यूरिंग नॉर्मल लोडिंग और पीक लोडिंग, this condition is always true, that with lagging and unity power factor connected at with lagging and unity power factor load connected at the end of the transmission line, it will have a positive voltage regulation. And the other thing was that the zero regulation or the negative regulation can come only in case of leading loads, only in case of leading loads. Okay, here we have found, now we have found conditions for zero regulation and for maximum regulation. So the conditions was like this, that for maximum regulation, what was the power factor angle required? It was required to be tan inverse XL by R, right? And for zero regulation, for zero regulation, phi R was tan inverse R by XL, right? This was equals to, I can say, theta, and this was equals to phi by 2 minus theta, right? Now what happens if theta is 45 degree? What happens if theta is 45 degree? If theta equals to 45 degree, तब क्या होगा? Then maximum regulation and zero regulation conditions coincide. These conditions coincide, which means that at this condition the voltage regulation will be zero only, right? And that will be the maximum regulation, ठीक है, यानी कि उससे कम हो सकता है रेगुलेशन, ठीक है, उससे ज्यादा नहीं होगा पावर फैक्टर उस पर चेंज करने पर भी. सो आई मीन लीडिंग पावर फैक्टर जब तक रहेगा, दिस विल बी, बिकॉज zero regulation can only come on the leading loads. So if both these condition of maximum regulation and zero regulation coincide at theta equals to 45 degree, right? So that will be all for this lecture. We will see the next thing, that is Ferranti effect, in the next lecture. Thank you.